In this video, we're going to take a look at some key properties of eigenvalues and, to a lesser degree, eigenvectors that are useful from a practical standpoint, but also from a theoretical standpoint. And these are done in no particular order. I'm going to state the properties and then give you kind of an outline of the proof so you can see why, right? Why this thing works, right? So the first one is this: if A is triangular, right? So if you have a triangular matrix, then the spectrum, which is a set of all the eigenvalues, so all that is, it's just your A11, A22, dot, 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 A, N, N. And I'm just using braces here to indicate that we're dealing with a set. And the way you can see something like this is if our matrix is triangular, it doesn't matter if it's lower or upper. So we know what it means. You know, you'll have your entries here, and then I'll do my dot, 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 since I'm not specifying the dimension. And then let's say it's upper triangular, so you'll have all your zeros here, and then you'll have whatever numbers above the main diagonal. So I'll just do a couple of things like this. And then, so this will be our A. And then if we do our process and do our A minus lambda I, what's going to happen is that we end up having A11 minus lambda, and then A22 minus lambda, all the way down to ANN minus lambda. You'll still have your zeros there, and again, all the entries that are above the main diagonal will remain the same, right? Because from those entries, you're just going to be subtracting 1. So our P of lambda, which is the determinant of this new matrix, because this is still an upper triangular matrix, the determinant is just a product of the entries on the main diagonal. So you'll have this, and then dot, 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 your ANN minus lambda. So therefore, what values of lambda are going to make this polynomial equal to 0? Well, it's each of the lambdas that would make each factor equal to 0. So you'll get that your lambda 1 is A11. Lambda 2 is A22, dot, dot, dot. Lambda n is your ANN. And some of these lambdas can be repeated, but the interesting thing here, and we'll actually use this fact later on, is that because we now know the roots, it actually gives us this, what we have here is the factored form of the characteristic polynomial. It just so happens that when your original matrix is triangular, the factored form is easier to come up with, right? But this factored form is very useful. And I just want to make a note here that this is an nth degree polynomial, right? And as we know, and once your degree gets larger and larger, finding roots can be tedious, right? But that one is really useful. Next up, let's look at the connection between eigenvalues, right, and another important number that's associated with a square matrix, and which just happen to be its determinant. So let me just kind of go back to our definition of the eigenvalue and eigenvectors. So this is our definition, and if you remember how we rearranged it, I subtracted the lambda v from both sides and factored, but there's no reason to, or there's no requirement, I should say, that we have to subtract lambda v from both sides. If we wanted to, we could do this. We could say lambda v minus AV is equal to our 0 vector, and then end up with this sort of factorization. So you'll have this lambda I minus A, that quantity times V, is equal to 0, right? And you'll see why I did it this way. So for instance, so since I want a connection between the determinant and these eigenvalues, I'm going to look at our characteristic polynomial, and I'm going to write it in two ways. So by definition, the characteristic polynomial is the determinant of this coefficient matrix. I'm just going to write it down over here. So it's the determinant of this other form that we just came up with, lambda I minus a. So we have this. But then there's another form, and I made mention of it right here about the factored form. Now, there's a theorem that says any polynomial of degree n will have counting multiplicities to n complex roots. And then once you know the roots, you can come up with what's called a factored form of the polynomial. So that's what I'm going to write down now. And the factored form would be something like this, where it's your variable minus each of the roots. Right? So this is the factored form, and then I'm going to do my dot, 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 and then I'll have lambda minus my lambda n. Right? So again, let me just kind of highlight what's going on here. This is by definition, right? And then this is not definition. This is a big thing. This is by what's called the fundamental theorem of algebra. Look it up. Fundamental theorem of algebra. Really useful, all right? Okay, so what is the point of doing this? Well, we have a polynomial. So let's see what happens if we evaluate both of these forms at lambda equals 0, right? So let me first do the, I guess the blue one, right? So which is this one. If I take that form and I do p of 0, what do we get? Well, if I plug lambda equals 0 in, I will have the determinant of just 0 minus the 0 matrix minus a, which is the determinant of negative a. And if you think back, it's been a while, but we had a property that tells us what happens to the determinant if we multiply our matrix by a scalar. That scalar, which in this case is -1, gets raised to the power that is the dimension of the matrix. It's going to be -1 to the n times the determinant of my matrix. Okay, so we have an expression like that. Let's see what happens if we take the red form now. Take this and evaluate that at lambda equals 0. So if I do this and plug 0 in wherever there's a lambda, I'm going to have 0 minus lambda 1 times 0 minus lambda 2 times dot, dot, dot times 0 minus lambda n. And what happens is I'll have negative lambda 1 times negative lambda 2 times negative lambda to the n. Now, I don't know how many negative signs I have there, so I don't know if they cancel out or if they reduce down to -1. But what I do know is there are n of them, so it's going to be -1 to the nth power times, and then I'll have my lambda 1, lambda 2 times dot, 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 lambda n. But what is this telling us? So what we've done essentially is we've expressed this polynomial in two different forms, right? But it's the same polynomial, and we evaluated both forms at the same value of 0. So this implies that the -1 to the n times the determinant of a has to be equal to -1 to the n times lambda 1, lambda 2, dot, 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 times lambda, and not a comma. These are all times. I don't know why I'm putting commas there. So that's all multiplying. And then what happens is the -1 to the n, it cancels out, and then we have this really important result that the determinant of the matrix is just the product of its eigenvalues. Dot, 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 lambda n, right? And sometimes a product, we use sigma for sum, we use pi for product. So another way of writing this is that the determinant of a is uppercase pi, I going from 1 to n of lambda I, right? So the result here is that the determinant of A is simply the product of the eigenvalues of A. Right? That's pretty important, right? So again, it just kind of lends more to this idea that these numbers, they say so much about the character of the matrix. All right. Third one is, now once we get a connection to the determinant, it then allows us to connect the idea of eigenvalues to invertibility. So let's talk about what we know about invertibility. So we know that A is invertible if and only if, that's what the double-sided arrows mean, right? The determinant of the matrix is not equal to 0. But we just said that the determinant of the matrix is always going to be the product of its eigenvalues. So then, if and only if lambda 1 times lambda 2 times lambda 3 dot 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 times lambda n, that's not equal to 0. So if you have a product of numbers that's not equal to 0, right? Once you're working in what's called a field, then none of these factors could be 0. So this implies that lambda 1 can't be 0, and lambda 2 can't be 0, and dot 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 lambda n can't be 0. So this shows a very important result, that A is invertible, right? If and only if IFF lambda I is not equal to 0. So this is another way of saying that 0 is not an element of its spectrum, right? So again, not having an eigenvalue of 0. I remember what that would mean if your eigenvalue of 0 is like it just annihilates the vectors, right? And you do have some matrices that do that, but the ones that do that, they would have to have 0 as an eigen, they would have to have 0 as an eigenvalue, which now is telling us that the matrix would have to be singular. So it's the singular matrices that would have the property where they can annihilate, just kind of zero out a non-zero vector, right? Invertible matrices don't have that power, if you consider that a superpower. All right, so there's that one. Just a couple more. So now that we've now linked to invertibility, let's see let's see a little bit more with invertibility. So let's go back to our definition. So much starts right here. So now let's add, let's say, suppose A is invertible, right? So now let's say A is invertible. That just means A inverse exists. And then by property 3, we know that lambda can't be 0, all right? So we know that. Well, if you have an inverse, think about what we've done with lots of like matrix equations when our coefficient matrix here has an inverse. We would multiply both sides by the inverse. So let's do that. Let's do A inverse times this, and then similarly A inverse times this. All right. And so because matrix multiplication is associative, I can group, instead of pairing up the A times V, I can pair up the A inverse times A, again, which we've done many times. And the scalar lambda is a constant, which I can factor out, right? I can factor out because I can, in this case, I can change the order of scalar multiplication and matrix multiplication. What I can't do is change the order of matrix multiplication. So I can take out the lambda, and then I'll have A inverse and then times V. And then on this side, look at what happens. We know that inverse times A is just going to give us the n by n identity. So we got that there. And then I have my lambda, and I have my A inverse, and I have my V. And then I know that the identity times our column is just going to give us back the same column. So I'll have V here, and then I'll have lambda, and then A inverse times V. And then because our lambda is not equal to 0, instead of multiplying the right-hand side by lambda, I can multiply the left-hand side by 1 over lambda. So I could do this, right? 1 over lambda times V is equal to A inverse times V. And then let me rewrite this the way we kind of started with our definition, where I have the matrix multiplication on the left. So this is just saying that if I now multiply by A inverse, what will happen is the scalar gets reciprocated. So if you notice, the vector is the same as the original vector that I have here, but now the eigenvalue that corresponds with the inverse matrix is the reciprocal of the original eigenvalue. So it basically says this. So if A is invertible with eigenpair, and I'll just say this is pairs, it's a little bit easier, with eigenpair lambda V, then A inverse has eigenpair 1 over lambda V. So the eigenvector is the same. It's just that now what the inverse will do, and if you think about it, the inverse is just going to undo what the original matrix does. So if the original matrix scales V by a factor of lambda, then its inverse, which we know now has to exist, we'll have to scale it by the reciprocal of lambda. Just so much geometry and cool algebra at play here. All right, so last one I'll just say, and this just this kind of extends what number are we at? We're at 5 now. I mean, we could go on and on, but basically, if we start with, again, same equation, so we have an eigenpair lambda and V. Instead of multiplying by A inverse, what if I multiply by A? So in other words, what if I did the transformation yet again? I applied the transformation multiple times. So if I multiply this by A, on this side I would have A squared times V, and then on this side I would have, let me write it like this, I would have this. And then again, just like we did with the scalar, we can put it in front, so we'll have lambda times AV, and then I know AV is just lambda times V. So I'll have lambda times V, which means I now am scaling by lambda squared. So if I apply the transformation 2 times, my scale factor gets applied 2 times. And similarly, if I apply the scale factor, the matrix multiplication or transformation 3 times, same logic here, I'll get that lambda cubed times V is going to be the same as A cubed times V. So to generalize this, we really need to use a process called mathematical induction, but I'm not going to get into mathematical induction. But at least for positive integers, right, we can see where if I repeatedly apply our transformation in the form of matrix multiplication, then the result will be that scale factor will be applied that many times. So in general, and really I should have by induction here and go through an inductive argument, which I won't do, but lambda to the n times V is always going to be lambda to the n times V, right? So again, the summary of this is, if lambda V is an eigenpair of A, then for n greater than or equal to 1, let's say as an integer, I'm going to say this, and here's the symbol for integer, I'll just do that. Or we could say a positive integer, right? So n greater than or equal to 1, then lambda to the n times V is an eigenpair of a to the n, right? So it's this idea of either repeatedly doing the same thing, which is what property 5 is referring to, or now trying to undo what you've done. And you can only undo it if you have an inverse. And this kind of gives you the relationship between the, um, the scalar and the inverse, all right? And there are lots of other properties. I'll just mention some that I'm not really going to write down, but you know the sum of the. In fact, let me yeah, I will write it down, but I'm not going to give a proof for this one. But the trace of your matrix is the sum of the eigenvalues. So it's like this, right? So the determinant gives you the product, or is given by the product of the eigenvalues, and the trace is given by the sum, right? And if you look at the 2x2 case, which we developed in a couple videos previously, you would see that relationship here. But this extends to not just the 2x2, all right? So there are some really useful properties of the eigenvalues, and if you continue to look deeper, you'll see so many other connections that relate to properties that we've discussed previously. So go explore, and hopefully I'll see you in the next video where we get to explore together.